In this video, we will talk about how to represent functions using power series. So in the last couple of videos, we talked about various mathematical functions that can actually be represented as a power series. And I use the term non-elementary function because sometimes functions are complicated. The real world, the interactions and the relationships in nature, such as beating on a drum head and watching the vibrations move, not necessarily representable using simple elementary functions. So actually, let me talk just a little bit more about what I mean by the term elementary functions, but it's something you can always Google if you're wondering what that means. But like all the functions that we study in like pre-calculus, algebra, calculus are referred to as elementary. So like, for example, any polynomial is what's called an elementary function. Any square root function, sine of x, cosine of, x squared plus 11, e to the x. Basically anything, logarithms are elementary functions, rational functions, anything comprised of division, any combination of any of those things, via composition, whatever. Basically, most of the mathematical things that we're used to dealing with in math class are referred to as elementary functions. So a non-elementary function is just something that basically it's too complicated to be represented using a lot of those fundamental mathematical components. So an infinite series is sometimes it is elementary, sometimes it's not. How do we know? Well, we'll get into that. But the Bessel function is an example of a non-elementary function because basically it's too complicated to be related back to a sine or cosine. It's kind of like this next level of difficulty, which is why the term non-elementary can be helpful. And in order to understand how non-elementary functions work, that's the importance of power series and knowing how to use interval and radius of convergence. Basically, everything we've studied so far helps us to understand these sorts of functions a little bit better. But actually, another very interesting idea is that you can actually represent a lot of the elementary functions using power series. And one of the fundamental ideas is because let's go back to the geometric series example, right? The very first power series I showed you was the general series 1 plus x squared plus x cubed plus x to the fourth. And again, you could think of this as a non-elementary function just because it's an infinite polynomial. But technically, this is equivalent to a rational function. And if you're like, well, how is this equal to a rational function? Because it looks like an infinite polynomial. But if you remember, what my argument here was that this is a geometric series, right? With a first term, a is equal to 1, and a common ratio r. But as we studied, right, we know that all geometric series converge if r is less. So if that ratio r, the absolute value of x, is less than 1, then we know that that's a convergent series, right? And we referred to that as the interval and radius of convergence of this particular power series. But more importantly, we know that a geometric series converges to a over 1 minus r. Remember, there's that formula, right? A geometric series we actually know the true sum of this infinite series. It's always going to be a over 1 minus r. And if we just plug in a over 1 minus r, well, a is 1, the first term, and r is the common ratio. Clearly, it's being multiplied by x from term to term. So what we get is 1 over 1 minus x must be the sum of all of those things. And essentially, let me highlight, because this is how my brain is imagining all of this, is that 1 over 1 minus x is equal to the infinite expansion 1 plus x squared plus x cubed plus x to the fourth. And basically, this is something that when I first kind of thought about it, it kind of blew my mind because it's an algebraic expression that involves literally infinite series of polynomials. And that infinite series has to add up to a different function. Like a series of sums can actually add up to 1 divided by 1 minus x. It's a very interesting idea as far as I'm concerned. And that's exactly what the formula here says. We have 1 over 1 minus x is equal to the sum of x to the n as n goes from 0 to infinity, which is equal to 1 plus x squared plus x cubed. But essentially, this is a formula which equates 1 over 1 minus x to an infinite series of polynomials. Now, before we work on this a little bit further, let's think about plugging numbers into this. And also, it's important to note that, let's go ahead and note over here that the IOC is minus 1 to 1. And all that means is this formula is only valid if x is between -1 and 1. If I try to plug in 5 for x, this formula is going to be crap. It's not going to make sense. And that, again, is the importance of the interval and radius of convergence. But let's say I'm plugging in a number within the interval of convergence. Let's say 1/3. Basically, I can pick any x I want, and this formula should be valid. So let's try it out. Basically, if I do 1 divided by 1 minus 1/3, what I would get is 1.5, or 3/2. Now, if I plug it in on the other side, I could do 1 plus 1/3 plus 1/3 squared plus 1/3 cubed. Now, of course, the difficulty of the right-hand side of this statement is it's an infinite series. So technically, I would need to keep going forever. But what it's saying is that if I keep adding this infinite series is equal to that specific formula. And if you're like, well, why? Well, we know this is true because it's a geometric series, right? And this, as we've practiced a geometric series, there's always a simple formula to see what it adds up to. Plus 1/3 to the 6, and so on, right? And if I keep going with that pattern, notice obviously I can't literally add to infinity, but I can go far enough to say, if I add the first 5 or 6 terms of this function, it's equivalent. But basically, it's an alternative form of a representation of a function. So before we look at how this can be useful, first of all, this is actually how a lot of calculators do a lot of mathematical calculations. Now, it's not how all calculators work. And if you're studying computer science, my guess is you'll probably find this very interesting. But basically, notice that on the right-hand side, we have a series of adding and multiplication, right? In order to do this, I need to add up a bunch of fractions and do a bunch of fraction math in order to solve this sum. But on the left-hand side, I have just a straight operation of division. Essentially, how I'm kind of imagining this formula is instead of doing this calculation, I can do this calculation. And sometimes certain calculations are a lot simpler in the form of arithmetic. What we're going to talk about in lab next week is how you can actually take other functions and represent them as series. That's what we call Taylor-Maclaurin series. And we'll get into that fundamental idea very shortly. But also, another thing about this is you can actually tweak the formula a little bit because basically this is equal to this, and other rational functions, like this is a very, very specific rational function 1 over 1 minus x. That specifically is equal to this sum of polynomials. But if you make an alteration to this formula, again, on the algebraic side, it should be consistent across the other side. And let me try to show you what I mean by that. But let's say we had a function f of x is equal to 1 over 1 plus x cubed. And let's say we wanted to know, how would I express this as a power series? Well, basically, I could use this formula, right? Because this formula says 1 over 1 minus x is equal to this. But here, if you're like, okay, this one's plus, how do I do that? But basically, how I would imagine it is there a way that I can write this function using the original formula? But I could write this as 1 over 1 minus negative x cubed, right? And if I write it like this, what I would have is 1 over 1 minus something. And basically this something, let me go ahead and highlight that. I'll highlight it and say yellow or orange or whatever, is basically replacing x in this formula. And if I use this formula, I could replace x with minus x cubed, and I could do the same on the other sides of the equation to represent this using a power series. Because what this says is that 1 over 1 minus x can be written as an infinite series. And, because of that reason, I could reuse this formula. So basically what I would have is I could rewrite this function as the infinite power series n equals 0 to infinity of negative x cubed to the n. And notice all I did here was, well, here I have 1 over 1 minus x. So how I'm kind of imagining is here's x, and that's x right there, right? So I'm just replacing, if I'm changing it to negative x cubed as it is in this function, I could change this to negative x cubed. Of course, this should be consistent, assuming we're within the interval of convergence. Or additionally, I could rewrite this as an expanded form. So this would be, the first term would still be 1, then I would have minus x cubed, then plus x to the 6th, then minus x to the 9th, and so on. And that series will continue. But instead of being a consecutive series of polynomials with coefficients 1, growing by a degree at a time, basically it will be growing by 3 degrees every time, and it will also be an alternating series in this polynomial. And essentially, basically what I'm just saying is like this would be referred to as the power series representation of this function. And again, if you're like, well, how do I know that this is true? Well, you could try plugging numbers in. But also, another thing is the interval of convergence for this particular power series representation. Since I'm using a formula where x is valid within here, what I would need to do is make sure that I'm changing this to x cubed, because basically this formula, I could rewrite this as absolute value x less than 1. But I would need to plug in the new x to make sure that the interval of convergence is not being altered. But notice if I replace this for its IOC, I would have negative x cubed is less than 1. Again, absolute value of a negative will be positive regardless. So what I would have is x cubed must be less than 1 and greater than negative 1. And if I took the cube root of everything, what I would have is essentially the same thing. But basically this would have the same IOC as the original, would be negative 1 to 1 for this power series, simply because it's going to match with this one. But it's something you can't overlook, and it is not always going to be the same. So actually in the next example, you see the interval of convergence is different. Let's look at why. So let's just do one more example, because again, this is kind of complicated in terms of we're using a formula to try to represent a function in another way. Notice, well, this rational function, 1 over x plus 4, also, again, it's not a minus, x is first, and again, you might be thinking, how would I actually write this in the form? But basically, I would think about it in terms of algebraic manipulation. I'm trying to rewrite it as 1 over 1 minus x if I was to use this geometric, expansion formula. So I could rewrite this as, well, 1 over 4 plus x, basically put the x second, that way it looks a little bit more like this. That's obviously equivalent. Another trick I could do is I could actually factor out 4 from the denominator. So I could factor out a 4, and that would leave me with 1 plus x over 4. And basically I could rewrite this as, well, this would be 1/4 multiplied by 1 over 1. And also notice that I have 1, and if you're like, well, why did I factor out a 4 there? It's because to use this formula, it needs to be 1 over 1 minus something. And again, I'm almost at that point. I have 1 over 1 plus something. I could obviously write that as 1 over 1 minus a negative x over 4. But basically, over here, now I have it in the proper form to use the formula to expand it. And let me go ahead and highlight again. Basically, instead of using x, what I would have is negative x over 4. And I could then substitute this in for x in this formula. Because again, this formula is true unanimously for any x, assuming it's in this interval. And I can always apply the formula to rewrite this in red as a power series. So basically, again, I could take this function, this other random rational function that we're looking at, 1 over x plus 4, and I could rewrite this as 1/4 times the sum of negative x over 4. Whoops, it's a weird division. 1 over x to the 4 to the n. And if I'm losing you, like, if you're like, how the heck, what are you doing? How are you doing this formula? But basically, I'm taking this expression here. Since this is 1 over 1 minus something, I'm just plugging it into the formula, which is that, well, I have 1/4 times this, which let's go ahead and circle it in red once again. All that is just by this particular formula, which is well known because essentially this geometric series can be written as a fraction, as a rational function. So you can think about that backwards, right? Any fraction can be written as a geometric series because a geometric series that converges is a fraction backwards. And, it's a very backwards way of thinking, but it's true. And it's very interesting because we can take a very specific rational function and turn it into an infinite power series. And this idea is very critical for establishing any mathematical function and taking it into a power series, which is something that we'll be doing very shortly, which is kind of like the most important idea in all of Calc 2. Or again, I could write this as an expanded function. This would be equal to 1/4 multiplied by, well, basically, instead of having 1 plus x squared, I'm plugging in negative x over 4. So I'd have 1 minus x over 4 plus x squared over 16 minus x cubed over 64 plus x to the 4th over, what's 64 times 4? 256, and so on. But essentially, I could take a rational function, represent it using an infinite series instead. And again, it's like taking a function in one form and representing it in a different form. And if you're saying how does this make any sense, it looks completely different. Well, that is exactly the nature of it. It's very weird, and we can demonstrate that this is true. But before we try plugging numbers into this, let's first again think about the interval of convergence. Let me rewrite that 4 because it's looking a little bit messy. But basically the IOC here, because again in general it was -1 to 1, but since I'm tweaking -x/4. Again, what I would do is I would plug that into the formula, right? Because generally it's true when the absolute value of x is less than 1, but I'm substituting x into -x/4. So basically this expansion should converge if -x/4 is less than 1. And again, if I apply the absolute value of a negative will be a positive, and this will be true in between -1 and 1. And notice that if I multiply through by 4, well, actually what I'll get is from -4 to 4. Basically, this will converge in a wider range than the original formula. Basically here, x could be anything from -4 to 4, and this formula will work. And actually notice if you think about that, this obviously won't work at -4 because it will be an undefined function. So clearly this will not make any sense. But again, basically the IOC here, the interval of convergence of this, tells us what numbers are valid, tells us what we're allowed to use, and if it's outside of the IOC, this power series will diverge. This formula won't make any sense, and as we know with the geometric series, it's only valid in certain numbers. It's always something that's important to consider. Okay, so let's just say, let's try -3, or I don't know, 3, whatever. But let's plug in some random number in the interval of convergence. So if I plug in 3 into here, well, what I would have is 1 divided by 3 plus 4. That's, of course, just 1/7. So basically 1/7 would be when x is 3. Now, if I plug in 3 down here, this series should be equal to 1/7. Let's try it out. So what I would have is 1/4 times 1 minus, what did I say? X is 3, 3/4 plus 3 squared over 16. And basically, if I continue this representation, 3 cubed, it should be minus 3 cubed over 64 plus 3 to the 4th over 256, and so on. Obviously, in order to properly use this, I'd need to go infinitely. But if, let's say, we use the first 5 terms, it should be a pretty decent approximation to 1/7. And obviously, we're not there yet. But essentially, if that series goes any further, that infinite series should add up to 1/7. And again, you might be thinking, why? Who cares? Like, why is this relevant? Why is this important? But it's kind of interesting because we can take any fraction. You could take any rational number and rewrite it as an infinite series, which at the end of the day, it might not seem very useful, but it is very useful. And we can do the same thing with sine, cosine, e to the x, and a lot of other mathematical functions as well. And it's one path towards solving integrals that cannot be done. If you remember what I said back when we were in chapter 7, sometimes when we're solving integrals, like say the integral of sine x squared, sometimes called a Fresnel integral with respect to x, sometimes these integrals have no, I said at the time, we referred to this as being unsolvable, or it has no elementary solution. Well, technically, these can be solved using an infinite series. So essentially, how it works is this function is elementary. It's sine of x squared, right? This can be represented using our elementary functions, but its antiderivative is non-elementary. It actually has an antiderivative that we can figure out, but it takes using power series and so forth to be able to solve. And, that's one of the main reasons in Calc 2 we learn about power series, convergence of series, and, representing functions as power series, because it's one thing that we get stuck on in integration, right? And in chapter 7, that was one of our goals. Like, how do we solve integrals? But basically, even if you're stuck, there's another way around it. And it's very difficult, but that's what we've been working towards for quite some time. Anyways, that will end up this video lecture series when we come back to class. When we come back to lab on Tuesday, we will start talking about what are called Taylor-Maclaurin series, which are also very, very interesting, very, very useful. Kind of similar to this idea here, where we're taking a mathematical function and rewriting it as an infinite series.